Okay, we're on. Hi, everybody. This is New England Dynamics and Number Theory Seminar. Moving to Hamburg for a while. The speaker now is Maxim Kirsebom from Hamburg, and this is a title towards an extreme value law for the deepest cusp excursions of the unipotent flow. So, Maxim, back to you.
Okay, thank you very much. So thanks to the organizers for inviting me to give this talk, which is very nice. So what I will be talking about today is joint work with Keivan Mallahi-Karai, who's also in the audience. He's from Jacobs University in Bremen. And it's kind of work in progress. So I gave a talk on this about a year ago where I said we hope to have a preprint on the archive soon. And a year later, I'll say the same thing and hope that this time it'll actually be true. So hopefully we soon have a preprint on the archive. The other thing I want to say here at the beginning is that almost everything I will be doing today is actually quite elementary, sort of in terms of methods and techniques, but sometimes you can do quite cool stuff with fairly limited means. So let me start by telling you the setting that I will be working in today. And it's quite a simple setting, or at least like quite a well-known setting to many people here, I suppose. So it's the unipotent flow on what I will call X, and X is SL2R mod SL2Z. I should probably say PSL2R mod PSL2Z, but I will be a little bit lazy and just leave out the P. Okay, so now this space is well known to allow two different geometric interpretations. I will use one of them to motivate the question, and then use the other one to actually state our result and also some previous results. So the first geometric interpretation of this space is that it can be identified with the unit tangent bundle of the upper half plane modulo SL2Z. So we see down here a picture of the upper half plane. We can't so well draw the unit tangent bundle, but we can kind of maybe imagine it. So once we mod out SL2Z, we get this fundamental domain F. And then if we look at a point here, Z comma V, so this is the vector V, which is a unit vector. And in this picture, we also often call it the horocycle flow, as the picture already suggests why. Because if we want to follow the unipotent flow, which starts at the point Z and flows like with direction vector V, what we need to do is to draw the horocycle that goes through Z in such a way that the vector V is orthogonal to the tangent. And then it's this horocycle has to intersect the real line in just one point. And then to get the flow, we simply flow clockwise along this horocycle until we hit the side here.
Yeah, you can check one.
At which point we emerge from the left-hand side and we continue flowing. At every point we have attached this unit vector, which is orthogonal to the tangent of the horocycle. And of course, what's going to happen then once in a while, we emerge here at the blue point and we will flow down and hit the bottom down here. And then there's a different transformation for how you emerge from the bottom. But the important thing in this picture for us is that, so once in a while, you will hit the bottom in a way where the vector that emerges from the bottom will correspond to a gigantic horocycle. And then when you flow along this gigantic horocycle, you will make an excursion deep into what we call the cusp. It doesn't have necessarily a well-defined starting point. We just kind of generally talk about it as this unbounded region of the space. And we know that almost every such orbit must be making increasingly deep excursions into this cusp because the unipotent flow is ergodic. And that means in particular that almost every orbit will visit every neighborhood of the space. So also every neighborhood in the cusp as far up as you'd like. Okay, so there's a general sort of interest in understanding these cusp excursions that could be either how frequent they happen or how long time is spent in the cusp or especially from our point of view, what is interesting is sort of the growth rate of like, so how fast do you get like very deep into the cusp? So I'll keep it vague for now. I'll just sort of state it as a general goal in this direction is to understand cusp excursions of the unipotent flow. Okay.
But do you talk about generic points, starting points, or all points? What does it mean?
Well, this is sort of deliberately kept so vague because I guess one thing that people, which I will also get to, is something like, say, a logarithm law will be a generic point, right? So that's an almost sure like statement about how almost every orbit behaves in terms of how it goes into the cusp. What we will actually be looking at today is a distributional result. Okay, but this is just sort of to, in the vaguest possible way, say what we're roughly interested in. Okay, so let me give the second geometric interpretation, which is the one we will kind of be working in mostly. And that is that we can identify X with the space of unimodular lattices in R2. So I'll denote that L2. And I have a drawing prepared here. So here we are in R2. This is an example of a lattice. We will often be denoting those by capital lambda. So this would have bases, and these would span a region of area 1. And so in this picture, it's like geometrically not immediately obvious what it means to go into the cusp along the unipotent flow, or for an orbit of a unipotent flow. Maybe let me first just quickly mention that in this setting, we can write the unipotent flow as it's a one-parameter subgroup consisting of matrices 1T, 0, 1, where T is real number. And this acts on L2. And I'll be a little bit sloppy in that I will also kind of refer to UT simply as the matrix and not the whole group. Okay, later. And yeah, I should also mention here important fact is that we have, of course, a harm measure here on this space. I think about it as a normalized harm measure, and that's UT invariant. Okay, and so what I was just saying before is that it's not obviously clear what it means to go into the cusp, but using Mahler's compactness criterion, it's also not too difficult to see that for an orbit of the unipotent flow, or basically the only way you can go into the cusp essentially is for your sequence of lattices to contain a short vector. Essentially, a vector going to 0 means going to infinity in this picture. So just very generally, we can sort of say that UT lambda cusp excursion in L2 that corresponds to UT lambda containing a short vector. Okay, so if we want to study cusp excursions in this picture, we want to study sequences of lattices with short vectors. And for that purpose, it's useful to define the following function. So I'll call it alpha 1. It's from L2 into the reals. And what alpha 1 does is it takes a lattice lambda, and it gives me the supremum over all lattice points in lambda that non-zero, and over 1 over the norm of V. Okay, so we see the supremum is realized by the shortest vectors in the lattice, because obviously if the vector is short, the norm is going to be small, so 1 over the norm is going to be large. Okay, so this is a very important function for studying cusp excursions. And that leads me to talk a little bit about what is sort of known about cusp excursions that is sort of interesting to us for the purpose of what we want to do, which I haven't really revealed yet, but is coming soon. Okay, so sort of the central result interesting for us was in a paper by Athreya and Margulis from 2009. And what they proved was that for almost every lambda in, so they proved it actually a bit more generally. So in Ln, we have that the lim sup for t going to infinity of log alpha 1 ut lambda. We divide this by logarithm of the time, we get a constant, so which is 1 over n. So this is commonly referred to as a logarithm law for the unipotent flow.
And n is 2 here.
Sorry?
N is equal to 2 here.
Here it's actually just, they proved it just, yeah, so the space of unimodular lattices in Rn. So if you, for our case, it would be exactly n equal to 2. So then we would have a 2 here.
Okay.
Okay, and so Athreya and Margulis also generalized this a few years later to more general homogeneous spaces. And that's kind of, from our perspective, what is known about the cusp excursions in the direction we're interested in. But there is, of course, the analog question for the geodesic flow, where a bit more is known, and which is kind of relevant because the unipotent and the geodesic flow are kind of very interlinked. So there's the analog question for the geodesic flow, and that has a bit of a longer history. As far as we know, it started with Sullivan in 1982. So he proved a logarithm law for the n-dimensional hyperbolic space mod gamma. Gamma is here a discrete group of isometries of the space. So that means that the space becomes finite volume but non-compact. And then he looked at the geodesic flow on this and was able to prove a logarithm law for the distance, the hyperbolic distance in this setting. This was generalized in 1999 by Kleinbach and Margulis. So there was again a logarithm law, but for more general homogeneous flows. So we see these logarithm laws that says something about how fast, maybe actually I forgot a little bit to say, maybe like sort of what's the interpretation of this logarithm law. Maybe I should say a word about that. So, well, basically what we say, right, is like, since we're looking at the lim sup, we're looking at these maximal excursions, and we sort of measure how deep the excursion is using log of this alpha 1 function. So we see if we do that and we divide by log t, we get a constant. So that's sort of telling us that the expected growth rate of a generic orbit of a unipotent flow will kind of get into the cusp at a rate of roughly logarithm of the time when we measure it with this log alpha 1 function. Yeah, and so maybe the general comment here is like this logarithm law can really be proven in very high generality, be proven to hold in very high generality. And so the geodesic flow in not so high generality, but like a bit more specific setting, a more precise result is known. So this was proven by Polycott in 2006, and it's a so-called extreme value law. And so you might remember that extreme value law was one of the part of the title of this talk. So that's kind of what we're interested in. So that's also why I would like to sort of describe this theorem in a little bit more detail. So this was for H2, so the upper half plane modulo SL2Z. In this theorem, UL is the natural volume measure on the unitangent bundle of what I call V here. Gamma T is the geodesic flow starting at Z with direction vector V. And H is the height above the horizontal line with imaginary value equal to 1. And with this notation, what Polycott proved was that for all R in R, the following limit, so if we take the limit t going to infinity, this measure on the set of points in the unit tangent bundle of V, if we consider the maximum for all times between 0 and capital T, where we consider the height of the geodesic flow at time t, and we ask the question, when is this less than R plus log t? So log t is here. Now I didn't state Sullivan's logarithm law precisely, but since he's looking at the hyperbolic distance, it's a little bit different than the Athreya and Margulis one. But essentially, in this setting, the logarithm law says that we expect log t to be the growth rate of a generic unipotent orbit. So we're asking the question here, which proportion of points does not manage to beat this expected growth rate by this additive amount R? And what it turns out is that this amount is e to the minus 3 over pi squared e to the minus R. Okay, so this additive amount R appears here on the right-hand side. So it's kind of a more precise statement than the logarithm law, because obviously, sort of any point that falls within this sort of this growth rate of log t plus an additive amount will still obey the logarithm law, but it gives us like quite fine information about how points distribute around this expected growth rate. So a couple of general comments here. One is that what we have here on the right-hand side is a Gumbel distribution. Maybe somebody has seen that somewhere in a statistics course, has this general form. And the second remark, which I kind of already made, is that, but also precisely, you can prove that if you have such an extreme value law, then it implies a logarithm law. So in the case of n equal to 2, and also when gamma is this SL2Z, we get, we recover, so to say, Sullivan's logarithm law. And then just a little bit about what has been attempted in this direction for more general homogeneous spaces. I tried myself to do this and got some partial results towards extreme value laws for more general homogeneous flow. So it was roughly the setting of the Klein-Bock-Margulis paper, for those who are familiar with that. Though it's really in this generality, it was at least I had to make a lot of rather complicated assumptions, so that the results in the end were quite dissimilar to, say, this Polycott result. And even then, you only get like upper and lower bounds on the on this limit. And recently, Björklund and Gorodnik have, so I don't think there's a preprint available yet, but they have made some improvements, so like reduced the number of assumptions needed. But in this level of generality, there's really not much understood about how these extreme value laws work. Okay, just to further explain a little bit, or how to understand this Polycott result, here's a picture again in the upper half plane, where we again have our fundamental domain. And in this case, log t is the sort of expected growth rate. So we would here look at here's like a random point, giving a random geodesic. And we're basically asking the question, has our orbit up to time t beaten r plus
So is everything okay? There is no sound for me either.
Analog.
Maxim, can you hear us?
Yes.
Okay. It's now back. We lost you for a moment.
Oh, for how long?
Right somewhere in the middle of this picture.
Okay, all right. Let me just briefly repeat. So this was sort of just to sort of repeat what this polycode result kind of says in sort of intuitive fashion. Here we have the upper half plane and the fundamental domain again, and pictured here is a random geodesic. And sort of the thing the polycode result tells you something about is what's the probability that this random geodesic has not managed to get further into the cusp than these thresholds that are depicted here in blue, red, and green. And you can basically, so these are our just examples of R values that I've chosen. But that's sort of, yeah, just to demonstrate this distribution around the expected growth rate of log t. And yeah, what I was saying afterwards was like this gives us like a concrete goal, and that is to try and get an analog of the polycode result, the polycode theorem for the unipotent flow UT on the space of unimodular lattices in R2. Okay. And I'm going to present today a partial result in this direction. We don't manage to quite get a full extreme value law, but we get part of it, which we'll see in a second. But before I get to our theorem, I just want to do a quick detour into extreme value theory or extreme value statistics, just to sort of tell you where these kind of problems come from a statistical point of view. So it is a subfield of probability and statistics, just where you try and understand these statistical limit theorems. So it's kind of like a sibling of the, maybe you could say a sibling of the central limit theorem. So the standard setup would be a probability space and a sequence of random variables, either a stochastic process if you're looking at it continuously, or a sequence of random variables if you're looking at it discretely. And then you define simply a new random variable, which is the maximum of these random variables. And then you ask, so the central question in extreme value theory is, can I find such a sequence here, UT of R, such that this probability, oops, that was the wrong thing, that one I wanted, so that the probability that the maximum stays less than this UT of R, when time goes to infinity, that converges to a non-trivial distribution function. And this UT of R is what, for example, in the polycode theorem is R plus log t. And this theory generally, if you have like an independent setup, so for example, in the discrete case, if you have IID random variables, then you get a very nice theory. Things are rather easy to prove. And it turns out that such extremes are rather well behaved. Then you can try and apply it to dynamical systems. There you don't have independence, but you might have some fast mixing. And part of extreme value theory basically tells you that, you know, there's some independence type conditions. If you can satisfy those, then your system behaves as if it were IID from an extreme value theory point of view. And there's been a lot of work in this direction the last couple of decades. I've mentioned some names here, and it's not a complete list, but some of the people who have been doing a lot of work in this direction. Mostly it has been applied to, extreme value theory has been successfully applied to interval maps with nice mixing properties. Not exclusively, but mainly. But so this is also kind of to say that the unipotent flow is not sort of an obvious candidate for obtaining an extreme value law, because for the unipotent flow, we only have very slow mixing. So it's not an obvious candidate, but it turns out that through some geometry of numbers, you can actually get quite far. Okay, so without further I do, I will let you in on what we are able to prove. So we have a theorem, and I won't give it a number because we only have one. So this is Mallahi-Karai, myself, and I hope that we can get it out this year. That should certainly be possible. Okay, and this theorem says in the setting that I've described, so unipotent flow on L2, our distribution function, which by definition is the limit for time going to infinity of the harm measure on the lattices in L2, for which the maximum from 0 up to t of this log of alpha 1 of ut lambda. So the probability that this is less than r plus 1/2 log t. Okay. And you might notice here already that we have this 1/2 here compared to the Polycott statement where it was purely log t. And that's because the logarithm law of Athreya and Margulis contains this. So it's a little bit different in that the logarithm law for L2 is equal to 1/2. So 1/2 log t is the expected growth rate. And the function you get here is a little bit complicated to write. So you get a function f1 of r, which is 1 minus 3 over pi squared e to the minus 2r. And this is the value of the function for all r positive. And then we get another function f2, which is 1 minus 3 over pi squared e to the minus 2r plus 6 over pi squared e to the minus 2r minus 2r squared plus 2r minus 1. And this is true for r values between minus 1/2 log 2 and 0. And finally, for r values less than or equal to minus 1/2 log 2, we unfortunately can't tell you yet what happens. You all still hear me, right?
Yes.
Okay, good. There's no further fallouts. All right, so this is a bit of a complicated expression. In a picture, it looks a little bit nicer. So we see here the f1 function for the positive values of r. This is f1. We see from how it continues here that it had to change at some point because otherwise we would hit 0 right away. So at this point, r equal to 0, we change into this for a short while we have this f2 function, which it also can't continue to be because that goes to infinity. So that's this function until here. And what happens after that is what we don't yet know. Okay, but actually proving this, I can almost give a full proof of this. At least I can give a very thorough sketch. And that's what I will use the rest of the talk to do.
Excuse me. Hello.
Yes.
Sorry, I have problem because I don't understand this difference, the 1/2. I'm not sure there is a difference between the log law. It's just a question of how you put the dimension, maybe. You see this 1/2 in the 1/2 log t. You said
Yes.
it's not the same in Polycott.
Yes.
But it is the same. Like if you had like geodesic flow on SL2R, you will still get the 1/2.
Yes, that's true. Yes, you're absolutely right. So
there is no difference because it's just a Borel-Cantelli lemma. So it has to do with the volume of the balls. So it is not.
Yeah, it's normalization of the measure, I guess.
Yes, it cannot be different from for the same dimension, it will be the same coefficient.
Yes, but so essentially the I guess the thing is if you look at the Sullivan logarithm law, right? It's stated as so I think if I had stated it appropriately, it says something like hn plus 1 gamma, and then
exactly, and then you get the 1 over n. Yes,
1 over n. Yes,
exactly.
So it's not different in, yeah, it's just essentially this result is, if I understand it correctly, it's one dimension higher than if you have the logarithm law on h2 mod gamma, right? Because if you have h2 mod gamma, you get here the limit 1.
No, it will still be, yes, and in fact, you have the flow, and for example, H2, the dimension is 3, because
Yes.
it's the flow on the tangent space.
Yes.
Anyway, I just wanted to say that there is no difference between the logarithmic law of the geodesic flow and of the horocycle flow. That's all. And then it's just a question of notation. And I agree it's a 1/2 here, but just not to say that there is a theoretical difference between the laws.
Yes, you're right. That I think, yeah, you're right. I said that in a confusing way. There's no fundamental difference. It's just whether you say, the two different sort of geometric interpretations I talked about, with the notation and the dimension and so on. But yes, you're right. Thank you for the comment. That's a good clarification. Okay, so the proof goes as follows. So we have the first step, and that's just to sort of simplify and reduce the problem. So we just say simplify. Okay, so what we want to do here is we start by defining the notation Et of R, and this is really just my set from my theorem up here. So I'm actually just gonna copy it. Okay, so this is the set that we are interested in estimating the measure of eventually. And first, really just through some very basic set theoretic manipulations, I can rewrite this set as the set of lattices in L2, such that lambda intersects the union of times between 0 and capital T, u minus T applied to the ball with center 0 and radius e to the minus r 1 over root T, root r. No, wait, sorry, 1 over root T. Yeah, that's correct, like that. And for convenience, I remove 0. And this has to be empty. So we're looking at the lattices that do not intersect this thing. Now this thing is a little bit complicated, so just to simplify notation, I will call this radius r, and this whole union I will call drt. Okay, so I've just rewritten the set that I want to estimate the measure of as the lattices that do not intersect this guy called drt. And then actually, eventually, it will turn out to be easier to estimate lattice points, like the probability of lattice points hitting drt. So I will say this is non-empty and add a complement, and then I haven't changed anything. Sorry? Okay, can't quite hear if there's a question. Okay, I will continue at first. Okay, so if we want to estimate the lattice point that do intersect DRT, we need to get a picture of what DRT looks like.
So what is the area? Do you know the area of DRT?
Almost. It's that's what we're kind of going to be estimating here. We're going to be getting a picture of the area of DRT by including it in a, like, we're going to include a smaller set and include it in a bigger set. And thereby we're going to see the difference going to go to 0. And then we'll know what the area of DRT is.
But if the ball is just, so the ball is Euclidean, it probably doesn't matter if it's Euclidean or...
Yes, it's just Euclidean, yeah.
So if it's in the supremum norm, that it's very easy to write it down.
Yes, but it's just, this is really just Euclidean sort of in R2, right? So,
okay.
Okay. Okay, so to do this, we certainly need to first have a look at what happens when we apply u minus t to some point. Okay, we get x minus ty and y. So that means if we have a point here that is sent, so if this is xy, it gets sent over here to u minus t of xy. And if we're in the lower part of the picture, it gets sent over here. So this is CW, this is u minus t ZW. Okay, so whatever this DRT ends up looking like, it's kind of clear from symmetry considerations that if we use the fact that if a vector is in lambda, then minus v is also going to be in lambda. So since the unipotent u minus t here does not change if you're in the upper half or the lower half, it means that if we have an intersection in the upper half, we'll also have one in the lower half, which means that we can basically ignore the lower half of the picture. So for simplicity, I will just ignore that. Then the picture gets a little bit simpler. Okay, so we can ignore the lower half here. And looking at the upper half, so this DRT will look something like this. And poorly drawn, but something like that, which is a little bit difficult to work with, right? So DRT will be this black area here. So what we do is we take, so we take this line that I had drawn here, and we call that IRT. I'm actually going to call it plus. I think to be kind of consistent, I should have now changed this to plus. I'll put a plus here, one there, and then one there, just to signify that we're in the upper half of the picture. Okay, and then this rectangle, the red rectangle, we'll call small ORT plus. And then we're going to apply u minus t to these two guys and take the union. So what we're going to do is we're going to define capital RT plus as the union over all times between 0 and capital T, u minus t of small I RT plus, and big O of RT plus is analog the union from 0 up to capital T, u minus t ORT plus. Okay, and in the picture, when one looks a bit at it, we can see that the capital ORT will end up looking something like this. So the everything here red belongs to capital ORT. So this is the red area. And we can do the same with the blue one here. That will look roughly like this. So everything blue will be the capital IRT plus, so blue area. Okay, and now simply from the picture, it's clear that we have that IRT plus is a subset of DRT plus, which is a subset of ORT plus. And what we're going to say now is essentially that the difference between ORT plus and IRT plus is going to go to 0. So we will eventually be able to substitute DRT plus here with IRT plus. So to formulate that in two small lemmas, we have one lemma, and these are like, they're almost too small to be lemmas, but it's kind of useful for reference. So if we have a set generally in Rn, which does not contain 0, then we have that the measure, so the probability that a lattice intersects B non-empty is less than or equal to the Lebesgue measure of B. So this is just a one-line application of the Siegel formula, which we will get back, or we will get to that a bit later. And the second lemma, which is almost proven by looking at the picture, is just that the Lebesgue measure of ORT plus minus IRT plus goes to 0 as t goes to infinity. Okay, so the difference goes to 0 in Lebesgue measure, and since the Lebesgue measure is larger than the mu measure, then the mu measure also goes to 0. So the difference goes to 0, which means that we can replace DRT with DRT plus with IRT plus. So let me write that as a conclusion here. So we conclude that f of r, which was the measure of ETR in the limit, I forgot the limit. And so that's equal to 1 minus, because we did this trick with the complement, we get 1 minus the limit mu on the lattices that intersect DRT plus non-empty. And what we have just shown now is that we can replace DRT plus with IRT plus. Okay, so far so good. That brings us to the second step of the proof. There will be 3 steps. And step 2, in step 2, we're actually going to be taking the limit in a bit of a funny way, at least for me. So we have the picture down here of, this is IRT plus. And when t gets very large, this becomes this triangle, which is stretched far out to the left and is of very low height. It's a little bit inconvenient to work with. So what you can do is simply to multiply it from here to there. We multiply with the matrix AT, which is 1 over root t. And so that's a small computation just to see that that stabilizes the triangle in the sense that it's now no longer dependent on t. So we could simply call this IR plus. But to use this for anything, we need a small lemma. But again, that's really just a tiny computation. I call it lemma C. Lemma C tells us that if we have a subset of Rn, so this is for any subset of Rn and any element in SLNR, when we look at the measure of lattices that intersect A non-empty, that's the same as the measure on the set of lattices that intersect G of A non-empty. But that means in particular that this thing of multiplying this AT has not changed our measure of the set that we're looking at. So we can conclude now that our f of r, 1 minus, and then we can see up here we had our previous conclusion. So here, this one we can replace by IR plus, and this limit we can remove because now the capital T is gone. So we have 1 minus the measure, the set of lattices that intersect IR plus non-empty. So maybe a small remark here. So just at least for me, this was it's kind of an interesting detail of this proof is that you basically take the limit by multiplying this matrix. Maybe for somebody in the audience, this is very natural. From a sort of probability point of view, this was rather surprising to me because it's not always trivial that these kind of probabilities, that this limit exists at all. And the fact that you kind of achieve it just by multiplying by this matrix was kind of, at least to me, somewhat a surprising, interesting detail. All right, I still have a little bit of time, so I think I'll make it. We have another tiny simplification. Many might know that when we write lambda star, what we might mean is the primitive points, primitive lattice points in lambda. Okay, so those are the points that cannot be written as an integer multiple of another point in the lattice. And there's another tiny lemma here to consider. That tells us that the probability that lambda intersected with, that lattice intersects our IR plus non-empty is the same as the probability that it has a primitive point in IR plus. So this follows in our case because IR plus is a convex set, but it's a very, very short little argument. And this brings me to the final step of the proof. And that's where we're going to invoke some geometry of numbers. So here we are going to compute f of r. So all I will need is the Siegel transform and the Siegel formula. So we'll have, if we have a map from Rn to R, we'll call the Siegel transform f hat. That's going to be a map from Ln to R. So it's actually the modified Siegel transform where we sum over the primitive lattice points. So it's given by, it takes lambda, and it gives us the sum over all primitive lattice points evaluated in our function f. Okay, so that's the modified Siegel transform. And then there's a Siegel formula coming with it, namely that if we integrate this f hat function, we get 1 over zeta. So in this generality with n, we get 1 over zeta n, integral of f with respect to the back. So this is a Siegel formula. Okay, and that's actually all we're going to need. So now we'll split into the cases. So we had one distribution function for positive values of r. Now this is the easy case. So let's, if you remember, we were looking at this triangle. Looks roughly like this. It had side length e to the minus r, e to the minus r. So when r is positive, obviously e to the minus r is less than 1, which implies that the Lebesgue measure of I plus, this was our IR plus. Okay, so that's 1/2 e to the minus 2r, which is less than 1/2. Importantly, that implies that the number of lattice points in IR plus is less than or equal to 1. Okay, and exactly, so that's what we're going to use. And
what is lambda here?
um,
Arbitrary lattice or generic lattice?
see, so well at this point, well, I should write it. So I wrote it a little bit short, right? So I think what I actually meant was that the set of lattices for which lambda intersected with IR plus is non-empty. This is equal to 1. Right? That makes more sense. I think. Okay.
No,
right.
Sorry, it's even more confusing. The number of lattices.
You mean the number of vectors inside lambda, maybe that?
Yes, thank you. The number of, that's exactly what I wanted to say. The number of vectors in lambda. I guess I can put the star here as well, such that, thank you, such that V, and I should, okay, this I had written in a poor way, so V is in there, and then I can delete this. Okay, I think I've written something correct now.
Okay, so intersection of lambda star and IR plus.
Yes.
So there is one point of intersection, but what is lambda? Lambda is
sorry.
It's going to compute the measure of these sets, of these lattices, right? That was the estimate on the measure before.
Probably. So that's why I'm confused.
Yeah, I know.
Yes, let me just hang on. So
you didn't fix lambda so far, right? You assume something about lambda?
Sorry?
Do you assume something about lambda?
No, so this is just lambdas in L2. So
this is for any lambda. So basically, if you can have at most one primitive point in that triangle for any lattice.
Oh, okay.
Simply because the measure is restricted by 1/2, right? So we have 2 points here. They will span an area just, yeah, okay. So I should point that out. So these two will span an area just smaller than 1, which contradicts the assumption that it's a unimodular lattice.
Okay.
Okay, yes, okay, that was a bit confusing. Okay, so at this point, we set our function to be the characteristic function on IR plus, and then the Siegel transform is then going to be the sum over these primitive lattice points. And then this fact here, so that's important here, is that we can then say this is exactly the characteristic function on the set of lambdas that have non-empty intersection, where the primitive lattice points have non-empty intersection with IR plus, right? So we said we can at most have 1 point in this triangle. So intersecting non-empty is the same as saying intersecting in 1 point. And that's exactly what the modified Siegel transform here gives us, right? So this one is true only for the case R positive. But then once we have that, we just integrate this equation, right? So the right-hand side will give us the measure on the lambdas. So this is exactly what we want to compute, right? So IR plus being non-empty. So that's now just the integral of f hat, applying the Siegel formula, gives us 1 over sigma 2 integral of f with respect to the back. So this is 6 over pi squared times 1/2 e to the minus 2r. So 3 over pi squared e to the minus 2r. And since what we were computing was 1 minus this measure, we conclude that our f1 of r is equal to 1 minus 3 over pi squared e to the minus 2r. Okay, and so I'm running out of time, and I kind of predicted that I would run out of time. So I just pre-wrote the argument for the other case, which is, to some at least, a bit more interesting. And I'll quickly go through that, if that's okay. So we recall the claim that in this, for these values of r, we got this distribution function. Now, I've written it poorly again, but so when r is larger than this, just e to the minus r is less than square root of 2. That means the Lebesgue measure of our triangle is less than 1. And that means that we can have now 2 lattice points in our triangle IR plus, but we can't have 3. Right? Before we could only have 1, now we can have 2. So that's so for any, so this is probably where I should say for any, and I should put a star here, lambda in L2. This is true. Exactly. Okay, so now in this case, this is what we want to compute the measure of. So that's the measure, the probability that we have 1 intersection plus the probability that we have 2 intersections. So we do the same as before. We take the Siegel transform and we integrate it, and we get the same result. But now we have the measure of this guy plus 2 times the measure of this guy, right? And we want the measure of this guy plus 1 time the measure of this guy up here. So we have a small problem, which we can fix if we have a second moment formula. So a second moment formula would look something like this. So we have the Siegel transform squared. And then when we integrate that, so this, when we square it, we get this characteristic function plus 4 times this. And when we integrate it, we get obviously this, the measure of this set plus 4 times the measure of this set. If we could find out what that is, then we would have 2 equations with 2 unknowns, and that's something that we can solve. There's been a lot of work on this higher moment formulas, this geometry of number setting. I don't have a good overview of everything that's been done, but here's one theorem that we've been able to use. So it's Kleinbach and Yu, I think from last year. I've copied in the theorem here. And here they give a second moment formula for subsets of R2. This S tilde is just the, yeah, so the basically minus S. And it looks a little bit complicated, but actually in our case, it gets very simple because first of all, this S tilde, so this would be our picture. This is our triangle, IR plus, and then this would be S tilde. So we see first of all that this area here is going to be 0 because they have 0 intersection. The area of our triangle we know, and then a small argument, which I've written down here as a small lemma, will show you that this sum of these integrals, you actually only get a contribution for n equal to 1. So this integral here is what you need to compute. So then the question is, how do you compute that integral? Well, you need to figure out what this set Ixn looks like. The definition is here, but it's a little bit easier, I think, to understand in a picture. So I've written again the definition here. In the picture, in our case, we see what you do is you take a point x1, x2 in your triangle. That's this point. Then you have to find this point, which in this case is this point. And then you need to multiply it by all values of n so all natural numbers not equal to 0. So here's, for example, 2 times that. Here's all integers. So here's the -1 times that point. And then at each of these points, you add t times x1, x2. So the infinite line parallel to the vector x1, x2. So these are the green lines here. And then what you need to do is figure out for which values of t they intersect your triangle S. And since our triangle is rather small, it's a fairly simple argument to show that only this guy here can possibly intersect our triangle. And in the picture I've depicted here, so it's in quotation marks because the set is actually the values of t for which it intersects. Okay, but this is the sort of the intersections we're looking for. We need to find the corresponding values of t for which that happens, and that we need to do for all elements x1, x2 in our triangle. And I'm not going to give the detail, but I guess I hope I've made it plausible that this is really just some messing around with some integrals and some geometry, and really nothing fancy happens here. And if you do that, you get this formula for this integral. And that is what you plug in to this question mark that I had up here. That gives you 2 equations with 2 unknowns. And that, I hope you believe me, that we are able to solve. And that gives you the expression for F2 up here. And now I'm also over time, so I will say thank you very much for your attention.
All right, that's great. Let's give a big round of applause to Maxim, maybe by unmuting ourselves. Any questions?
Thank you very much.
I have a question. In fact, it's like a comment question. So what I like in this result is that there is something a bit frustrating in the beautiful theorem by Jadaev and Margulis, that what is frustrating is that you don't see any difference between the horocycle flow and the geodesic flow, right? Because they have the same log excursions. And based on that and the belief that there should be something different between this exponentially mixing system and the other one that is not that mixing, not that rapidly mixing. So what we did with Dolgopiat and Liu is we started looking at the multiple excursions, and for exponentially mixing systems, we found the logarithmic law for the not the extreme value, say, but the number 10 or R. So we, for an exponential mixing system, we kind of extended the Sullivan's law and the Polycott-Gumbel distribution for not the highest score, but the number R. And R is arbitrary finite number. And now, why did we start all this? Because we believe that we would be able to show that the horocycle flow does not have the multiple logarithmic law, that it takes a lot of time for the horocycle flow to go back to this log. So there is one thing is that you can at time t go to log t, and there is another is compute what is the frequency of such times? Like how long should you wait between the time t1 that this happened and time t2? For example, is in the horocycle flow, maybe t2 is exponentially exponentially big in t1. And that's my question is, can one say something about not just the fact that it's a log law, but how frequent do you bypass high log t?
Yeah, that's a good question. I don't know if I can say anything intelligent about it at this point. not sure on the spot I can see how I would formulate it in. But so does this do you get, if you know something about this sort of the second maximum and the third maximum and so on?
It's related. The two problems are related. If you know something about the second maximum, maybe you know something about how long does it take you to do the logarithmic excursions several times. But it's not exactly equivalent problems. They have connections. But yes, and there is. It's not easy to know what is the second maximum by this. The Athreya Margulis. It's very geometrical. You find one point and the lattice, but I don't see how you can control several times.
Okay, because I'm kind of thinking like, let's just say the second maximum would wouldn't it just correspond to, let's say if I go back up to somewhere here. Let's see, right? So I said like this is where we start. This is so if you have the second maximum, okay, so this set here gets somewhat more complicated because you have a union of two sets essentially, right? You have like essentially your set is the lambdas for which the first maximum is larger than your sequence, which I'll call UT, and the second one is less than UT, right? Yeah, okay, so I think this is different. So this is essentially an intersection, right? And so as long as you don't have fast mixing, it's always difficult to split these intersections. Exactly. But I wonder if, so this is why I, like this whole thing surprised me that it was possible to get anything at all, because I thought like, I was so used to thinking like you have to somehow invoke a rate of mixing and hope to get something. And we don't use, like there's absolutely no mixing here at all. So in this argument, so I wonder if like, if I do this rewriting, what would this set look like, right? And is that something that we can reduce in a geometric picture to something simple? It's not impossible, but I don't have a good, I can't say anything more intelligent than that, but it's a very, very good question.
Yes, it was just to...
yeah, thank you very much.
And I have another question that is maybe here, and this is maybe everybody knows, but I don't. So when you take a geodesic flow, you take this excursion, you go up, you reach, say, log t, then you take, then you will start going back, and you will enter the compact part before making a new excursion. So you know exactly how long you spend at height, say, log t before time t. So what about unipotent actions? If you say you can go to height log t, do we know that, do we control the gaps between the times where we, like, does it take time r? So you go to height log t. Can you say that you don't spend too much time there? You have to go back to the compact set before you.
Depends on the setting, right? I mean, like for the upper half plane modulo SL2Z, I'm pretty confident that that's the case, right? Like that can't really. There's only one way of going to infinity, but I guess once you get in higher dimension, the problem is that you have different ways of going to infinity, and then it's not quite clear.
Yes, I would like to have like gaps of order powers of t, say, for example, just powers of t. Like, you don't spend more than a power of t up there. You have to go back.
Okay.
I don't know if this kind of statement is true.
For the periodic case, you can embed everything in a nice Markov chain and all these calculations acting on the tree, and all these calculations become more transparent in the periodic case.
Okay, but this for you, I mean, many specialists here about unipotent actions, you're not sure there is a needed aspect.
Yeah, I mean, so I think, yeah, at least I can't really be classified, I think, as an expert on the unipotent flow. I don't know much more than than what I've been telling today, actually, about the unipotent flow. But I think there must be some people in the audience who know much more than me. But yeah, I don't know, at least.
But which flow we're talking? Is it still SL2M?
We can start with this 1,1T, and just say, okay, you go. We know by the logarithmic law that will go up to height log t before time t, say. But can we say that we come back to the compact set before time square root t before you then go back up?
Yeah, so if it's just in dimension 2, probably something can be said. You have a vector which is small, then this vector starts getting less small or a bit larger, but then some time should pass until the next vector gets small, basically. So it's just as elementary as what happens in this.
And for general unipotent, you think this would be a bit more complicated to have estimates?
Yeah, for general unipotent, you can have many small vectors at the same time. So basically, it's this non-divergence technique of Margulis, which I mean, some kind of inductive argument. So you have to bunch up those vectors, look at the some kind of planes which get smaller. But eventually, so there is a theorem that the flow spends a lot of time in the compact part.
Yes.
Maybe
I want to control the gaps, but okay, I will, when I have more precise maybe question, I will send it to you. Anyway, that was nice to see that at least now we know that there is some difference between the horocycle flow and geodesic flow, statistically speaking.
Yes, certainly. But yeah, that is a very good point. Yeah.
Yeah, that's very. So kind of continuing your line of thought, if you want to hit other values of R's, you have to look at the cases where you have 4 lattice points, 5 lattice points, and so on.
Yes, exactly. So I guess the suspicion is that let's see, if we look at the picture here, that you'll get, yes, a new function for even a shorter bit, and then a shorter bit, and then a shorter bit. I think we did actually prove that that for, like, you never hit the real line at any point. You keep above it, and I guess that the sort of the heuristics is, as you say, if we look at this triangle, say down here, right, the next step would exactly be to say, so side length √3. So then in that case, you can have 3 but not 4 lattice points. And but then, yeah, so you'd need a higher moment formula each time. And I don't know exactly what the status is for lattices in R2. So somehow, like, I guess there's maybe hope for doing this in higher dimension, in the sense that I think my feeling is that the higher moment formulas in higher dimensions are at the moment further than for lattices in R2, right?
I think there's a work of Schmidt about moments which might be applicable.
Yes, that's true. There was a paper by Rogers, and there was subsequently one by Schmidt. Yeah.
Michel, because he told me about this.
Yeah. Yeah. The only problem I have had a look at it, but I haven't gotten far with understanding it, unfortunately. But I have seen people commenting that sort of fixes the whole higher moment thing, but I haven't really figured out how, and whether we can actually then the question is, of course, also if we can compute what needs to be computed. So using this theorem of yours with you, like, you know, once you figure out this picture at the end, then it's just some pretty basic integrals to compute. The question is, of course, even if we have a higher moment formula, maybe whatever you need to compute is extremely complicated.
That's true. That's likely, yeah.
So,
okay, so it's some kind of, so you expect some kind of continuous function with infinitely many pieces. Given
yeah, that seems to me to be like a sensible conjecture. Well, maybe I shouldn't say it, but like at least a suspicion is that each time that you can have one more lattice point, the formula sort of has to change. And at least, well, I mean, this is just sort of the case here. Obviously, we have this part is, you know, also contained in the second function, and then something is added. So one could suspect that F3 would be F2 plus some higher order term. But yeah, I don't. Yeah, it seems natural. I don't have a much stronger reason to suspect it than that.
Okay. Any other questions? In fact, we are out of time, so let's thank you again. Nice talk.
Okay, thank you very much.
And I hope to keep seeing everybody for the rest of the semester.